rearrange it into a rectangle and a triangle and that feels more comfortable for you, go for either one. You don't have to know both, you just have to know this is the one I'm good at, this is the one that I'm comfortable with, I'm going to get my answer this way. But those are the shapes that you could be responsible for knowing the area for. Unless it's very close to the beginning of the test, it's likely to use that area in conjunction with something else. But that is the baseline information that I want you to have memorized or be familiar with. All right. For the rest of the time, we're going to be going over problems that I thought were interesting. They might be difficult, they might not be, but they're going to help you remember, oh yeah, this is something that I can do, or this is a tool that I have available to me. So the first one is a question 10. So very close to the beginning of the test. We're given a parallelogram, and we're told two angles. We have 25 and 55, and they ask us what is the measure of WXY. Feel free to drop it in the chat, yell it out. What is our angle measure? 100. So remember that WXY, tracing the angle, we're talking about this angle right here. And faster version is to remember in parallelograms that opposite angles are congruent. Slower version, still good, but good for the review, is to remember that parallelogram means we have parallel lines. And we're working with that idea that parallel lines are cut by a transversal. So if we talk about these parallel lines, and it's cut by this transversal, this is also 55. Again, not the fastest way to solve this problem, but I wanted to take the opportunity to review. And parallelogram, parallel lines, these are also parallel. This is our transversal, 25, also 25. Triangles add up to 180 degrees. 25 and 55 are 80 of those degrees, leaving 100 left for that other angle. So parallel lines cut by a transversal, really good thing to know. Triangles add up to 180, good thing to know. Parallelograms have parallel sides, good thing to know. And those opposite angles are congruent, good thing to know. Other one with parallelograms that might show up is that those diagonals bisect each other. So those would be the stuff that I want you to remember from parallel lines and parallelograms. All right. Next question. This is a number 13. We have in the figure below triangle ABC. So A, B, and C. And ABX are both right triangles. If the length of AB is 6, it's not given in the drawing, but it's easier for me to just write it in, but you would have to do this yourself on test. AB is 6 units, BX is 10, and XC is 4. what is the length of BC? And again, this is given in simplified perfect answer, not decimal. For the first one, I would prefer it if you can do this without the calculator. 6 and 10, it's a variation of their favorite Pythagorean triple of all time. If you have not yet committed it to memory, please do so. 3, 4, 5 shows up all over the place. They really like it. It's just a nice, easy, perfect right triangle. And so if we have 6 and we have 10, 6 is 3 times 2, 10 is 2 times 5, this is 4 times 2, or 8. And so we have 6, we have 8 plus 4 is 12, and we have our unknown. Again, no, never mind, that won't work. Distracted for a second. So here we are going to have 6 squared plus 12 squared is 36 plus 144, which goes to 180. Nothing to do with angles at all, just a coincidence that it happens to have that number. Your brain kind of will get jarred by a second, but coincidences happen, and so don't get distracted by that. What does the square root of 180 simplify to?
6 square root of 5.
6 square roots of 5? I agree. And that is letter E on there. That was question 13. Honestly, a little bit difficult for question 13. Around 13, you usually have a one-step Pythagorean theorem problem. That one threw 2 steps at you. That's okay. But again, I picked these for their teaching moments. Sometimes with the Pythagorean theorem, it's just recognizing the triple. Sometimes you have to run the numbers. In general, probably 4 times out of 5, they leave it in that perfect simplified answer, not the calculator. For people who are not confident with simplifying radicals, I tell them to run the radicals through the calculator and try and get it to match their answer. But for you guys, I'm expecting simplifying radicals is no big deal. So be confident about them. All right, 23. We have a volume of a cube. And so it says, if the volume of a cube equals 64, what is the shortest distance from the center to the base? This one should be 30 seconds or less. So volume of cube, what is the shortest distance from center to base? Well, first of all, what's special about a cube?
All equal sides.
All equal sides. In fact, the term cubed in math, what does that tell us? If we have a number cubed, what's happening to it? Number squared means raised to the second power. What is number cubed? To the third power. And so if our volume is 64, our side length to the third is equaling that 64. And so what is our side length going to be? 4. So if we imagine our cube, this side length is 4, but we're talking about the distance from the center to the middle of the bottom. Doing a bad drawing here, but we'll make it work. And so we're looking at the center of the cube to the center. How long is that going to be? Just halfway. It's the exact middle of that cube. So if we slice it in half, it's 2 distance from the middle to the center. So that's working with the idea of what cubes mean. They actually like cubes a lot. We're going to have more of them come up in this stack, but just being confident with what's going on. All right. The right triangle, LMN, is shown, and here's L, N, and M. We're told that this hypotenuse is 22 feet, and that the cosine of L is equal to 3/4. How many feet long is the segment LM? How would we go about finding this? You are used to finding cosine of number and typing that into the calculator. Cosine of 50 degrees, cosine of 32. Here, it doesn't matter what the angle was. They're giving you that answer. And so if you typed whatever angle L is into the calculator, it would give you 3/4. But working with this, if we look at the cosine of L according to our drawing, the cosine of L also equals adjacent, our question mark, forgot L, cosine of L, over our hypotenuse, 22. So the cosine of L equals 3/4, the cosine of L equals unknown over 22. We just set them equal to each other. 3/4 equals the thing we're looking for over 22. And it's a cross multiply and divide problem. And so even if they don't give you the angle measure, if they tell you straight out what the cosine equals, you just set that equal to the other ratio. All right. In that case, it does leave it as a decimal, and that is okay. Classic problem. I don't expect it to be very difficult for you. I just need to check in and remind you that it exists. If a triangle has a side length of 4.7 meters and 9 meters, which of the following cannot be a length of the third side? This is not restricted to right triangles, it's any triangle, but which one of these cannot be the third side of the triangle? don't know, take a really good guess, but if you're feeling confident, what have we got?
14.
14. The reason why is if we imagine 14 as this long side, because it would be the longest side, if we reach from one side and go 9 units, there's going to be another 5 units left over. And that's just to make a straight segment. 4.7 doesn't even reach all the way to meet it. And so we don't have a triangle. What we have is a segment and 2 little arms that don't reach each other. And so that one's called the triangle inequality. Keep it in mind of that is a real possibility. So again, that one was problem number 28. Oh no, that one was problem number 29. Started shuffling to the back rather than setting them down. All right, segment addition again, so getting comfortable with those segments. Points A and B lie on segment AD. So, now I'm going to do alphabetical order and give you a picture. A, B, and C, and D. AD is 32 units long. AC is 23. And BD is 27. How many units long, if it can be determined, is BC? This is problem 31. We are about halfway through. There are a couple different ways to solve this one, but the technique that I want you to be introduced to that can kind of be a faster way to go at this is the overlap. AC and BD overlap by the amount BC. And so if we unstacked them to just this length and this length, the amount of overhang is going to be that amount BC. And so just take 23 plus 27, that's 50, and subtract the original length. So if we added these two together, if we unstacked them and lined them up side by side, they would be 50, but it's only 32. So that means there is 18 amount of overlap. All right.
What question was that one?
That one was 31, so we're right about the middle now. We've hit halfway. We have 2 circles that are centered at the same spot. Sorry about my egg-shaped drawing. They are centered at the same. But we have X in the middle, Y on the first smaller circle, and Z on the second larger circle. And in the figure below, both circles are centered around X. The length of XY is 2 units. And the length of XZ is 6 units. If the smaller circle is cut out of the larger circle, how much of the area in square units of the larger circle will remain. And so this is the drawing they give you. I would give myself a really quick just pencil shade that I'm looking for this area. And now it looks like a donut. So how would we go about finding that area?
Subtracting.
Yeah, we need big circle minus littler circle. So what's the area of our big circle?
36 pi.
Are you giving final
Oh,
answer?
that's fine.
Yeah. So we have r squared is 36, and then pi, and then our smaller one is going to be 2 squared, or 4 times pi, and we end up with 32 pi. Again, default to leaving it in terms of pi. If they tell you to round your answer to the nearest hundredth, or if you look at the multiple choice and see decimals, then I'd do the calculation, but I get in the habit of stopping here and looking to see if they've offered that answer before you type it in the calculator, because frequently you'll end up going back and needing to go, oh yeah, it was that thing before I hit the calculator button. So that one is 36, getting along the test now. Again, be very confident about the area of circles. It will come up in some form, I just can't tell you which form. So now, question 40, similar to our parallelogram question, but now we have a trapezoid. So we're still in quadrilaterals, but we've switched up our information. So we have a trapezoid. It's not necessarily isosceles. My drawing happens to look that way, but it's not necessarily that. But we have 75 degrees here. We have a diagonal drawn in with a 25 and an unknown. We know that this exterior angle is 125. And we are trying to find the measure right here. How'd you get 30?
Let me do it again.
I don't know, I haven't calculated this one out. It might be right, it might be wrong, but that was fast, so I'm curious about your technique. I'd like to hear it.
Wait. Yeah.
So we have somebody here in person who said 30 really fast, and that is the correct answer, but have you figured out how you did it so fast?
Yeah.
All right, talk us through it.
Both the top and bottom lines are parallel.
Okay, so that is absolutely true. We have a set of parallel lines.
And so 125 equals the obtuse angle.
Yes, so we're treating this like a transversal and we have alternate interior angles. This is also 125.
And 180 minus 25 minus 125.
Yeah. So after that, you were adding up the triangle, and this was 30 degrees left over for that angle. I've seen it a couple different ways. That one's definitely the fastest one. I've had people who remember, oh, parallel lines, and they go for 180 over here, and then they solve that triangle. But that one is definitely probably the most efficient. Saying definitely, probably. All right, but yes, trapezoids also have that parallel. They don't give you a whole lot of parallel line cut by a transversal plane or cold, but they do give you a lot of it hidden within other shapes that have parallel. And so definitely still use those. That one was a 40. So another one that I hope is very quick, I'm just using it to touch on the topic and make sure you're reminded of it. In the standard XY coordinate plane, we have 2x plus 2 for our first equation, or our first line, and it wants a parallel line through the point of 3, 4. And so how would you go about finding the equation of the line parallel to that line through the point 3, 4? More coordinate based than something that we've done before, but coordinate geometry is still geometry. So, first question, what makes parallel?
Same slope.
Same slope. And so the 2 means absolutely nothing. We're interested in a line that has the same slope. And so y equals 2x plus our y-intercept. And we replace y and x with our numbers. We're replacing y with 4. We're replacing x with 3. And now it gets really easy. What will be our value of b? Minus 2. And so our equation is y equals 2x minus 2. So remember, parallel means that they have the same exact slope. They're moving the same way. Also, quite possible to get one with perpendicular, and perpendicular will have the 2 conditions. You have to do both of them. You have to change the sign, opposite sign, and you have to flip the fraction. And so our perpendicular slope would have been negative 1/2. Right. Again, another 41. Apparently 41 is a great time to have geometry questions. We have a drawing that looks like this. It's 14 across the top and 5, 2, 4, 3, 4, 4, and unknown. And the question is, what is the perimeter in inches of the figure? Go ahead and raise your hand online if you've got an answer. It's all right if you don't. This is a classic case of easy hard. Very, very easy if you know the trick. Really diabolically difficult if you are not catching on. The problem is, if you want to find perimeter as a add up all of the pieces, there are pieces that you cannot know in this drawing. This and this are both unknown. And so very easily, it could be redrawn like that, and it's still exactly true according to the drawing. And so you can't know how long these segments are. But if you look over to the other side, we could move this segment over and have 4. We could move this segment over and have 3. Now, how long is that side? 12. And the same way, we can move this segment over, and now we know something about the whole thing. What does the whole thing have to equal? 12. The same way, we can know this 4, and we can know this 2, but we don't know this piece. You could go to the trouble of calculating it out by taking 14 and subtracting 2 and 4 and the other 4, but in reality, we don't need to know that piece. We just need to know the whole thing. How long is the whole thing? Same as above, 14. And so this is just 12 times 2 for the two sides, plus 2 times 14 for the top and the bottom. We don't have to know all of the pieces to understand perimeter is the whole distance around. And so don't get bogged down in those details, when in reality, you just need to know what it adds up to, what the total is. And so any shape where you get these L-shaped cutouts like that, you can just turn it into a rectangle by moving the pieces, because we're only interested in the distance around. We're not talking about the area. The only time that is not possible is if you had something with a U shape like that. Then moving things around would mess with that total distance. So, anything perimeter with those L-shaped cutouts, kick the sides out. It makes it a much easier problem. Okay, that was 41. 45. Little bit back into trig. Trig is going to happen again. If we have y equal to the sine of 2a, what is the smallest possible value where the sine of 2a reaches its maximum? Have you done anything with trig graphs yet? Sine waves. So, very much in the transformation camp, I want you to be really familiar with the standard sine graph that it goes from +1 to -1, and it takes 2 pi to get there. That's your baseline that you should remember and be familiar with for trig functions. So, what would this 2 do?
Double the height.
No.
Double the length?
Because it is inside, if it were out here, that's how we would change the height. It changes the amplitude, it stretches it vertically. Because it's inside, it
Okay.
doubles every input value you do. If you put in 2, it's gonna act like it was 4. If you put in 1, it's gonna act like it was 2. And so what it does is it makes this move twice as fast. And so before it took us 2 pi to get to the end, now it's only gonna take us 1 pi. Bad drawing, but you know. It goes twice as fast, or half as long of the period. So before, this one happened at pi over 2. That was our original high point. Now it's going to be, cut that in half, pi over 4. Not particularly common. I feel like I see something to do with a sine graph once out of every 5 tests. So, 1 in 5 chance you'll see something with the sine graph. If you are interested with that, I think it's on page 4 of the notes, but I just wanted you to see it was there. In general, they tend to fall with the transformation rules more than anything else. And so if you see a sine graph, it's either going to just be reading it from the picture and working with it in a picture, or it's going to be something about transformations. So that was problem 45, but more rare. All right, we are running out of time, so I don't want to do that one. I'm trying to find a good one. All right, this one is trig again, but just something to get familiar with because it's not truly hard, it's just kind of weird. So if the sine of an angle theta is equal to 4/5 and theta is in between pi over 2 and pi, what is equal to the tangent of theta? So you don't have to be amazing at the unit circle, but this pi over 2 to pi, which quadrant is that going to be in? The second. So remember we have 0, that pi over 2 was where that sine wave was equal to 1, pi was back down to 0, 3 pi over 2 is down at -1, and then back to 0. And so it's wrapping around this circle. So if we're in between pi over 2 and pi, we're going this way. And they told us that the sine was 4/5, so our opposite is the 4, and our hypotenuse is the 5. Working with this triangle, what's this other length going to be?
-3.
3 length, but -3 as a coordinate. But 3, 4, 5, again, those triangles come back over and over and over again. So, the tangent is going to be our opposite of 4 over our adjacent -3, or -4/3. All right. Time for one more. That one's another stacked one. Alright, we're gonna pick this one. Last problem. So, the measure of the vertex angle of an isosceles triangle is a plus 30, and the base angles each measure 2a minus 15. What is the measure in degrees of one of the base angles? So here we have our isosceles triangle, and they want to know what is the measure of one of the base angles. How would you go about solving that? So first and foremost, with isosceles, remember that if the sides are the same, the base angles are the same. And so this angle up here is the vertex angle, or a plus 30. Our two base angles are 2a minus 15, but both of them are the same. And so if you added all those angles up, you would get a plus 30 plus 2 times 2a minus 15, and it still equals the 180 of the whole triangle. So it gets very solve heavy, but you need to understand isosceles triangle, these angles are the same, the vertex is itself. So, real quick, we'd end up with 5a, and plus 30 minus 30 disappears. And so it's just 5a equals 180. Divide both by 5. What do we get?
30.
Because it goes into
36.
gotta finish off the problem. 36. So, again, ACT, it's going to offer the answer to you. Don't be too quick to answer. It offers you 36, but what did the question ask for? It asked for what was the measure of one of our base angles. And so you'd have to do 36 times 2, 72, minus the 15. So make sure that you finish the answer that is asked. All right, we are out of time. That was a good lesson. I hope that it helped you remember what you have already known.